Hello everybody. In this lecture I'm going to go through electron configuration and I will show you how to fill in orbital or how to distribute electrons inside those orbitals. And I start with this, that we said when n equal 1 we have only one orbital, L is equal to 0, and we call it 1s. We show it by one box and we can have 2 electrons inside that box. I'm going to put 2 electrons here in it. When n is equal to, possible answers will be 0 and 1. That means we have 2s and 2p. 2s we show it by one box. You can put 2 electrons in it. Here is 2s and 2p. You can accommodate 6 electrons in it. So that means by end of second period, we are dealing with 10 electrons. 2 plus 2 plus 6, 10 electrons. When n is equal 3, we have L equal 0, L1, and L2. That means 3s, 3p, and new orbital, which is a 3d. I'm going to show just the d orbital, and d orbital is made of 5 boxes. You can accommodate 10 electrons in it. The 3s you can put 2 electrons, 3p you can put 6 electrons, and d 10 electrons. So now we're talking about 18 electrons for just the third period. When n equal 4, you have L equals 0, 1, 2, and 3. That means you have 4s, 4p, 4d, and new orbital, it will be f, for f orbital. F orbital is made of 7 boxes. Yeah. 7 boxes. You can accommodate 14 electrons in it. Yeah, 14 electrons. Okay, so now I can, start with any element, put the electrons inside the first available orbital, and move on. And I need to say this one: as we go up, as n is going up, energy is increasing. So that means, like, if you have one electron, you should put that electron in the lowest orbital, because it's going to cost less energy, or the system, it will have less energy, it will be more stable. So always you start with the first available orbital. So something that I need to mention it here, as you see, from n2 to higher, we are dealing with 2 or more orbitals. The way I showed them, I showed all of them same level of energy. Okay, so I wrote all same level. If this is the energy here, energy for 4, energy for 3, and that is for 2. And this is not true. In reality, this is not true to say that all this orbital, 2s and 2p, are on same level of energy, or in case of the n equal 3, 3s, 3p, and 3d are in same level of energy. This is not true. Okay, when you are dealing with empty orbital, true, you can say it. When you are dealing with empty orbital, there is no electron, then whatever you see is correct. Okay, but if we don't have electron, then there is no electron configuration. Then that means we don't have anything to talk about it. So this orbital are theoretical, okay, theoretical stuff, and in theory we say they are on the same level of energy. But when we introduce energy or electron, story is going to be way different. and I want to talk about that. I go with here. First thing that you need to know, effective nuclear charge. Okay, effective nuclear charge is equal to Z minus S. What's the Z? Z is number of protons. And S, we say shielding electrons. Okay, shielding electrons, or for now you can call it charge screened by other electrons. So I need to talk about this one. So effective nuclear charge, or the charge that one electron will fill, is going to be equal to number of protons inside the nucleus minus shielding electrons. For example, let's say you're talking about this nucleus, that it has 3 protons. First level of energy, when n is equal 1, you can have only one s, and one s it can have 2 electrons. Okay. So here, first electron, let's say second electron is there. These 2 electrons can see the nucleus directly, so they can see protons directly. There is nothing between the protons and electrons. This electron under huge force of the nucleus. Same thing with electron number 2. But the second you introduce a second layer, n equal 2, then here you will have the third electron. Third electron is going to see the nucleus. It will see the nucleus, true, but also it will see inner electrons, or it will see that electron. Okay. The inner electron, it will shield the nucleus. So the inner electron, it can be here, it can cover the nucleus, so the third electron is not going to see the entire positive charge of the nucleus. We have 2 of them, so I can say the effective nuclear charge in this case is going to be equal to number of protons. We have 3 protons minus number of shielding electrons. I have 2 inner electrons, so I say 2. It's going to be plus 1. So the last electron, or the third electron, is going to see only 1 electron. That's a 1 proton, sorry. 1 positive charge. Is not going to see the entire, the entire number of protons. So that means the third electron is under less force from the nucleus. The less force you apply, a higher freedom you give the last electron. So the last electron, it can go a bit far from nucleus, and this atom gets bigger, and we will talk about it in this chapter. So the effective nuclear charge is telling you what force you have, how much force you have between nucleus and electron. Let's say this one is F1, that one again is going to be F1, and same level. If this one is F2, F2 is going to be less than F1, because inner electrons will cancel some of the positive charge, and they don't let the outer electron to see the entire positive charges. Okay, so when we are dealing with atom that it has 2 or more electrons, then we will be dealing with a couple of interactions. First interaction, between any proton and an electron, we have attraction force. That's true. Why? Because two particles with opposite charges. Okay, so that's an attraction force. But the inner electron, it can see the outer one and it will repel it. This is repulsion. If you call it F3, F3 is repulsion. So we have repulsion or we have interaction between two electrons, and that's a repulsion force. Okay. The more inner electrons you have, the more shielding effect you will see. And also, if you have more inner electrons, that means outer electrons will see more repulsion force from the nucleus. And I'm going to go through all of them one by one. So when we have nucleus with two or more electrons, as I said, we will be dealing with repulsion between electrons. And the repulsion can be between inner electron, outer electrons, or between inner and outer electrons. And we need to take care of all those, or consider them in our actually discussion. First thing, that force is equal to K Q1 Q2 divided by R2. So if you have a nucleus that it has +2 charge versus nucleus that is a +3, in that case, you say the one that it has higher number of protons, is going to apply more force to the electrons. And this is true. Okay, this is true. So if you have electron here and the third electron, let's say there, if you're talking about electrons that belong to the second layer, you go with F equal to K. Q1 is the electron. Choose any one of them. Let's say this one. Multiply Q2. It will be number of protons. We have 3 protons. Divide by R2. For this one, we have F equal to K. Q1 is the electron again. Multiply Q2. This time we have 2 protons. Divide by R2. Okay. We have more positive charge inside the nucleus, so force is going to be higher. Okay. So F3, it will be higher than F2. First thing that, again, we need to consider is the charge of nucleus. A higher charge you have, more force you can apply. Okay. +3 versus +2. +3, it has higher force, so it will attract the electrons, or it will pull the electrons with higher force. That means they get closer to each other. If they get closer to each other, then those electrons start to see each other. And if they start to see each other, they will repel each other. Okay. So first thing, charge. Okay. Consider the charge of the nucleus. Next is the shielding effect. I mentioned the shielding effect. Okay, I have a nucleus with, let's say, 2 protons. So we'll have 1 electron here, 1 electron there. Next one, we have nucleus with 3 protons. We want to talk about shielding. Shielding effect, it says more inner electrons you have, higher shielding effect you will see. Right now, these 2 electrons can see the nucleus directly. because they can see the electron nucleus directly, there will be no shielding effect, and effective nuclear charge will be Z minus S. Z is number of protons, we have 2, minus inner electrons, we have 0, so it will be plus 2. How about this? Effective nuclear charge, it will be equal to 3 protons minus how many shielding electron or inner electrons we have. When I say effective nuclear charge, I'm talking about the force that we are applying on the last electron. Okay, force that we are applying on the last electron. So effective nuclear charge for electron number 3. Okay, so it will be 3 protons minus 2 inner electrons plus 1. So that means the last electron, it will feel less force from the nucleus. Okay, as you see, shielding effect in this case, it kind of like you feel is opposite the charge. Okay. So more protons you have, the higher attraction force you apply. The size is going to be smaller. You will have repulsion between electrons. That's true. Now, when it comes to shielding, it says the more inner electrons you have, the higher shield effect you can apply. So the nucleus, it will be covered by inner electrons. Imagine the nucleus is covered by a cloud of this 2 electrons. They will cover the nucleus, so the outer electrons will not see the nucleus directly. It will see whatever left technically, and it sees only 1 electron. Okay. So the more shielding effect you have, less force you can apply on the last electron. The next one is the penetration. And penetration, here the way I'm going to show it, let's talk about 2s versus 2p orbital. And I'm going to show it by drawing a radial distribution graph for each orbital. Start with 0. That's R, distant, 0, R. 0 means the nucleus. We're talking about nucleus here. And this is psi 2, or probability of finding electron. Radial distribution graph for 2s, it will be this. And radial distribution graph for 2p, this is 2p orbital, and that one is a 2s orbital. Okay. Now, next thing that you need to do, find the biggest area, and next find the maximum point for it. The biggest area here is this one. The maximum point is there. So I'm gonna go down across this one, and then choose this one and go down across here. If you just simply compare these two orbitals, as you see, the max point of 2p orbitals is closer to the nucleus than the max point of the 2s orbital. 2p is closer to the nucleus than 2s. Because it's closer than 2s, so first assumption is that give the electron to 2p orbital if you have to choose between 2s and 2p, because 2p is closer to the nucleus. But we have something that we call it penetration, and penetration is here. This first bomb. This area is kind of forbidden area for 2s orbital. we should not have a chance to find the electron in this area when it comes to 2s orbital. But apparently we do have. Electron it can show up close to the nucleus, and because this R is really small, this R is really small, that means the energy is gonna be, you know, like the force is gonna be way higher, and electron is close to the nucleus. Because it's close to the nucleus system, it will be really stable. Okay, electron can show up in an area or in a distance that is so close to the nucleus, and because it's so close to the nucleus, the system is going to be really, really stable. We call this one penetration. Okay. So 2p, 2s orbital, it will be lower in energy than 2p orbital because of this tiny bomb. We don't have it when it comes to 2p orbital. Okay, we just barely started, going up. We started getting chance to, actually to find electron. Well, this one is bigger when it comes to 2s. We say penetration. It will make energy of 2s orbital lower than 2p, even the maximum point of 2s comes after maximum point of 2p. So if you have to choose between 2s and 2 orbital, you put the electron inside 2s and not the 2p. Okay. So I have to go with 2s. So from now, I'm going to say, whenever I want to consider 2 orbitals that they are belong to same level of energy, I need to consider the penetration. If there is penetration, then be careful about it. Okay. We start with n equal 1. We have only one orbital. Only one orbital, and that orbital is 1s. And we know as we go up, energy is increasing. So you want to choose one orbital that it has the lowest n. That means 1s always is going to have the lowest energy. 1s, it will have the lowest energy. And then you go with n equal 2, you will have 2s and 2p. When it comes to 2 orbital that they belong to same level of energy, if you want to order them based on energy, you go with L. L here is 0, L is 1. The one that has lowest L will be the most stable orbital in that level of energy. So that means 2s always is going to be less than 2p in energy. And then n equal 3, you go with 3s, 3p, and 3d. So it will be 3s is the lowest, then 3p, and then 3d. Okay. Again, if you want to compare 2 orbitals that they belong to same level of energy, they are sharing n, you have to look to L. The one that has the smallest L is going to be the most stable orbital. And if you are considering orbital different level of energy, for example, 3p versus 2s, in this case, I look to n n equal 3, n equal 2. So we will have 3p higher level and higher energy than 2s. Sorry. So 3p will be higher energy than 2s. Okay, so let's review whatever I said till now. If we are dealing with different n, okay, n's are not same, like 2p versus 5d. You want to order them based on their energies. You go with n. The one that has the lowest n, it will be the most stable orbital. So 2p, it will be lower in energy than 5d. Okay, so you can say energy of 2p less than energy of 5d orbital. And if we are dealing with same n, like let's say 5s versus 5d, this time n equal 5, n equal 5. So you cannot use n, you go with L. L equal 0. How do I know L equals 0? Because it's a s orbital. This one L equal 2 because it's a d orbital. So I'm gonna say energy of 5s is less than energy of 5d orbital. In this case, you will start with 5s first, and then you put the electron other orbitals, like 5d. First one here, we said 2p is less than 5d. You go with 2p orbital, you fill in the 2p orbital. If you have something between them, you fill those orbitals, and then you go with 5d. Now, when we move to n equal 3, like we start to see some, facts that they are kind of against whatever I said. Now I want to tell you why you see, that kind of pattern. Okay, again, I said I need to consider penetration. If I have penetration, I need to be careful about it. We have 3 orbital, 3s, 3p, and 3d. And if you draw the radial distribution graph for them, you see the maximum point of 3s here, 2p, 3p, and that's 3d. Okay. Based on the maximum point, you expect that 3s, it will be highest energy expected. Okay, the expected one, it says 3s, it will be higher than 3p, and the 3p higher than the 3d. But only orbital that does not have penetration is the 3d. Okay, 3d. Look to the 3s. 3s, we have this bump, that's the second one. The first bump belongs to the 3s orbital and is the closest bump to the nucleus. And because of this tiny one, 3s orbital, it will be the lowest in energy. And after that one, we have this, okay, this one that belongs to the 2p. Sorry, 3p. 3p orbital. That bump or penetration belongs to the, again, 3s orbital, which I already mentioned it. And after that one, we will see a 3d orbital. So penetration made the 3s orbital lower in energy than the 3p and the 3d, even the maximum point, or R for 3s is the longest one or the biggest one. So you expect the 3s to be in higher level of energy, higher energy, okay, but it's not, and that is because of the penetration. So till now I'm talking about n equals 3, and we were sharing n, okay. But when it comes to 4s versus 3d, you will see that 4s is lower in energy than the 3d. And I told you, like, this one sounds like maybe opposite of whatever I said, because I said if we are sharing, if we're talking about different ends, then you'll consider the lowest end. Lowest end is 2 versus 5, because this one is 2, so it will have lower energy than the 5d orbital, which is comes with n equal 5. Okay. So based on this one, based on this theory, I'm talking about 3d versus 4s. So 4s should be higher in energy than the 3d. Okay. Because we're talking about n3 versus n4. But the reality is not, okay? It's not, and we need to talk about it. Why is not? Okay. And we say it's because of the penetration. Okay. From here, when you hit N3, you're done, okay, or you're close to be done, or you reach 3D orbital. After 3D orbital, we're supposed to have 4s orbital. You will see the gap between 3D and 4s is not going to be huge. Let me show it in here. Okay. If I move from N3 to N4, okay, from N3 to N4, I'm moving. Gap between, those two orbitals is not huge. Okay, it's not huge. So let's assume here is the 3D orbital, and then we have the 4s here. This is the gap between them. Let's assume. Okay. When you draw the radial distribution graph for 3D orbital, total nodes, it will be 3 minus 1, 2 nodes. You don't have any radial node, you have only 2 angular nodes. And this is the radial distribution graph of 3D orbital. And now if you show the 4s, it has 3 radial nodes. Show it by one bump. That's the second. The third one. Okay. Actually, I need to go one more. My bad. I need to go one more. Yeah. Because 1 node, 2, 3 nodes. Okay. As you see, maximum point of the 3D is closer than the 4s. So you expect the 3D to be lower in energy than the 4s orbital. And I told you, when we are dealing with different ends, we go with the lowest n. Okay. But then when I look to the penetrations, I see I do have penetration here for the 4s orbital. This penetration, it will make energy of the 4 orbital lower, or it will bring it down a bit, and it will bring this one down, let's say, right there. Okay, so now this one, it will be the 4s orbital. Okay. What's happened with the 3D? Nothing. 3D stay as as it was. The only change that happened is the 4s got lower in energy because of the penetration. Okay. So now we need to say that 3D is 3D. It has higher energy than the 4s orbital. So if you have electron and you need to choose between 3D and 4s, you have to go with the 4s orbital. Okay. When should I expect this one? From n technically 3, from n3, then you will see that 3D it will be higher in energy than the 4s orbital. Should I expect same, like same thing for 2p, for example, versus 3s? No, the gap between them, the gap is so huge that penetration cannot pay off that one. Okay, this gap is small when it comes to n3 or higher, and penetration, it can pay off this gap. When it comes to n2 versus n3, the gap is huge and penetration cannot pay off that gap. Okay, so from now, anytime we are dealing with d orbital, we will write it after s orbital. Okay. And the way I'm going to show it, I'm going to say n equal 1, I have 1s orbital. N equal 2, I have 2s and 2p. N equal 3, I have 3s, 3p, and now new orbital, it will be 3d. N equal 4, I go 4s, 4p, 4d, and now new orbital, it will be 4f. So as you see, always you start with s, and when you increase n, you will introduce new orbital. So from n1, I had only one orbital in s. n2, again, I start with s, but I introduce new orbital, p. n3, I have the s, I have the p, and now new orbital is d. N equal 4, we have the s, we have the p, we have the d, introduce new one is the f orbital. Okay, I want to follow whatever I said. First, if you have different if you have orbitals that belong to different ends, go with the smallest n. If you have orbitals that belong to same n, go with the lowest L. And the way I do it, I will pass one vector from this orbital. Okay, and this one started from nowhere, from nucleus, let's say, pass 1s. Write 1s. Pass second, or draw another vector parallel to the first one, and let it go, and pass the 2s. So I wanted to draw it parallel to the first one. Start from here, pass 2s. Okay, next one started from 2p, I say 2p, and then 3s. Okay, look for now. For now, it said n equal 1 versus n equal 2. N equal 1, it has lower energy than n equal 2. So I need to write the 1 as low first because it has less energy. Now, we have these two orbitals that belong to same n. This one L equals 0, that one L equals 1. you will write the one that has lower L. So you go with S because L equals 0, and then P, L equals 1. Then I will write the 3S because it has N equal 3 and higher than 2. So it will come after 2p orbital. And check this one. Fourth vector is passing the 3p. Again, L0 versus L1. And after the 3p, we have the 4s. Not the 3d. Not the 3d. Right, the 4s. And after that one, you'll have the 3D. So as you see, 3D showed up after 4S. And that was because of the penetration that I mentioned. And I said 4S, it has penetration close to the nucleus, and that penetration, it will make the gap here. It will pay off this gap, and it will make the 4s orbital lower in energy than the 3D orbital. Okay. Keep these two in your mind. When it comes to d orbital, for d orbital, write this, n-1 d. And for f orbital, we go with n-2 f. And for d orbital, we start with n equal 4. If you have n4 or higher, then you will have d orbital. And I say 4 minus 1, it will be 3. D, so it will be 3d orbital. And in this case, the lowest n you can have is going to be 6. From n equals 6 or higher, then you will be dealing with f. So it will be 6 minus 2. It will be 4 f orbital. Okay. So when I hit n equals 4, I need to write the d orbital. If I hit n equals 6, I will write the f orbital. And I go with this. 1s with 2 electrons. 2s, 2, 2p, 6, 3s, 2, 3p, 6. Now I go with the d4 with the 4s. So here 4s 2. I hit n equal 4 because I hit n equal 4. Now I need to introduce the d orbital, and it's gonna be n minus 1 d orbital. The highest n is 4, so you go with n minus 1. 4 minus 1, it will be 3, and that's going to be the d orbital, and we can accommodate 10 electrons inside d orbital. Okay. So it will be 3d10. Okay. And after that one, I go with 4p 6, 5s2, and then again I reach the s. I need to introduce the d orbital. It will be n minus 1, highest n, it will be 5, so it will be 4d10, 5p6. Now we go with 6s2. We reach n equals 6. So now we need to introduce the f orbital. For f orbital, we said n minus 2. So it will be 6 minus 2. It will be n minus 2 f orbital, and we can accommodate 14 electrons in it. So it will be 6 minus 2, 4 f 14. Next one, it will be n minus 1 d orbital. So it will be 6 minus 1, 5 d 10. Now I need to have the 6p p6, and after that one 7 s2 5 f14 6 d10, then 7 p6, and after that one I go with 8 s2. You need to have idea about this one to track the electron configuration. And I go with this. I'm dealing with electron, okay, and I want to distribute this, electron inside, and I want to distribute the electron inside these orbitals. I need to know, each orbital is made up how many boxes. If I have 2 or more boxes, how should I distribute the electrons inside those boxes? Okay, so we're going to talk about electron configuration. What's the electron configuration? It's the way we distribute the electrons inside orbitals. Okay, and we will be showing it by stuff like here 5s2. 5 represent level of energy, s the orbital, and 2 number of electrons inside that orbital, and we call them electron configuration. Next thing that you need to know, for naming any orbital, we said we need to have 3 quantum numbers, n, l, and ml, when you want to name one orbital. So for naming orbital, we need to have 3 quantum numbers. When it comes to electrons, you need to have 4 quantum numbers, and the 4th one we go with n, l, ml, and the new one is gonna be ms, or spin of electron. Okay, spin of electron. So this one, spin quantum number, ms, it can be plus half. The plus half, we show it by arrow that's pointing up, and second one will be minus half, and we show it by arrow that's pointing down. You can assume that you are dealing with magnet, that the north side here, north up, south down. In this case, when the arrow is pointing down, north is the bottom and south is up. Okay. If you put 2 magnets, that both are pointing up, you will have NS, NS. These 2 magnets will repel each other. Okay, those 2 magnets will repel each other. Well, if you keep the one pointing up and the next one pointing down, or you flip the direction, so in this case, this one is pointing up and this one is pointing down. And for the second one here, for this one, we will have attraction force. Well, the first one was repulsion. And this one is a new law that we call it Pauli exclusion principle. So the Pauli's rule says do not pair 2 electrons with the same spin. Okay, do not pair 2 electrons with the same spin. He said you cannot have two electrons with 4 identical quantum numbers. That cannot happen. Okay. Simple way of saying the principle, the Pauli exclusion principle is do not pair 2 electrons with the same spin. Why? As I said, because you will have 2 magnets that their north-north are front of each other and south-south, close to each other. Those 2 magnets, they will repel each other. If you flip them, north it will see the south and south it will see north, so they will attract each other. That's the reason behind it. And question is, why do I show electron by a magnet? Why do we do this one? Electron is a particle and it has a charge. Any particle with a charge, when it starts to move, it will make a magnetic field. That's the reason they said do not get close to cables with high voltage, because those cables, they have a magnetic field around them, and if you stay for a long time there, your body is going to feel that magnetic field and it will do interaction with the magnetic field, so you should not be there. Okay, so he said do not pair 2 electrons in one orbital with the same spin. You cannot have plus plus or minus minus half. This is wrong. You have to flip one of them. Okay. And he said you cannot have 4 identical quantum number for them. Okay. Let's say you have 2 electrons, electron number 1 and electron number 2, and we have only one orbital, and that orbital is 5s orbital. Okay. So we're going to put the first electron inside 5. And for electron number 1, it will be 5. And for electron number 2, it will be 5. If you want to put it here, again, it will be 5. Okay. Then what's the L? L for electron number 1, because it's the s orbital, it will be 0. How about this? This one also, it will be 0. What's the possible answer for ML? Well, L is 0. Again, it's 0. ML also, it will be 0. So till now, I have 3 identical quantum numbers, 5, 5, 0, 0, and 0, 0, 4 ML. 3 quantum numbers. He said you cannot have 4 identical quantum numbers. Here, the fourth one is going to be the spin of electron. For the one that is pointing up, it will be plus. MS for the second electron. He said you cannot put a plus. You cannot use a plus for this one, because if you do it, then you will have 4 identical quantum numbers. In order to fix the issue, we need to use opposite spin, and we show the opposite spin by vector that's pointing down. So this one, it will be minus half, and that one, it will be plus half. As I told you, simplest meaning of the Pauli exclusion principle is like do not pair electron with the same spin. And next rule that you need to know it is the Hond rule. Hond rule, it says electron, it has a negative charge, and if you put it close to another electron, you will have repulsion. It will have repulsion. Pauli rule, it says when you pair electrons, you have to pair them in a way that the spins are opposite. Okay. Because those 2 magnets will attract each other. That's true. They will attract each other. But does it mean we don't have any repulsion? No, you do have repulsion. You do have repulsion. Under any condition, there will be repulsion. But the attraction force is higher than the repulsion force. That's the reason we don't see, repulsion. But doesn't mean there is no repulsion. So if you have a way to minimize that repulsion, do it. And the Hund rule. Hund rule says if you have 2 electrons and you want to put them in an orbital like P or, for example, D, the way you have to distribute them, you start with 1 electron in each orbital. Do not pair them. So, for example, if I have only 2 electrons, and I want to put them inside this orbital, is that if you pair them, this is going to be wrong. You have to give each orbital 1 electron first, and if you have one more, then put it inside the last orbital, and after that one, you will not have any option, then you will pair them. Okay, so he said, distribute the electrons in a way that each orbital has only 1 electron, at least only 1 electron, because in that way you're not pairing the electrons and you got rid of the repulsion, or you minimize the repulsion. You minimize the repulsion. So we will pair them if we have to. Okay, if we have to. So for example, if I have 4 electrons, what's the solution? I go 1 in each orbital. Now for the 4th one, I don't have option. Then I will put it there. I don't have option. So this one will be correct. But if you draw it that way, here, this is gonna be wrong. Or let's say I don't know, like that one. That one also is going to be wrong. Okay. So distribute them in a way that each orbital has only 1 electron, at least 1 electron. Okay, so now that I know the Pauli and Hund rule, I'm going to start, working on the electron configuration. And I go with here, atom like lithium. It has 3 electrons, so it will be 1s with 2 electrons, 2s, 1 electron. How about carbon? We have 6 electrons, 1s, 2, 2s, 2. Now 2p, it will be 4. Sorry, my bad, this one is 2. It's a group 4. 2. Let's show the orbitals. We have 2 electron s, 2 electron in 2s, and p orbital for carbon. I put 1 electron in each. Okay, I put 1 electron in each. I do not pair them. So this one, it will be correct. How about oxygen? It will be 1s, 2, 2s, 2, 2p, 4. For carbon, for oxygen, inside p orbital we have 4 electrons. We go 1 electron in each. So now all orbitals are half occupied. We don't have option. We need to pair this one. I don't have option. I have to pair it. Okay, and I have 2 electrons here, 2 there, and 4 inside p orbital. So for oxygen, I said we have 8 electrons. We go with 1s2, 2s2, 2p4. For helium, it's 1s2. There's a way to kind of like write the electron configuration in a shorter version by using noble gases electron configuration. Look to this one. That is equal to helium. So for oxygen, I can say oxygen is equal to helium plus 2s and 2p4. This one we call it short electron configuration. So this is going to be the short electron configuration. How about sodium? Sodium is 11. It will be 1s2, 2s2, 2p6, and then 3s1. Write it for neon is 1s2, 2s2, 2p6. So we can write sodium equal to neon, and then whatever left, which is a 3s1. This is the short electron configuration of sodium. So this one is the full electron configuration, and this one is the short electron configuration. Full electron configuration. Well, this one is the short one, okay? So short electron configuration versus the full one. Okay, I want to go through stuff like valence electrons versus core electrons. Valence electrons, electrons that belong to last shell. We call them valence electrons or last level of energy. Core electrons, inner electrons, are the core electrons. So valence electrons are the electrons that sitting inside last level, last layer, and inner electrons are the core electrons. For example, you have nucleus with 11 protons. First layer, you will have 2 electrons in it. Second layer, you will have 8 electrons in it. So till now 10. And the third layer, we have only 1 electron. Number of electrons inside last layer, n equal 3, represent valence electron. So we say valence electrons equal to just 1. We have only 1 valence electrons. Core or inner electrons. Core electrons or inner electrons, whatever left. Totally we have 11 electrons. One of them is valence. Leftover it will be 10. 10 core electrons or inner electrons. I'm going to show core and valence electrons through electron configuration. If you are dealing with element that the last orbital S or S plus P. S or S plus P. In that case, just add electrons of S to P, and that one it will give you a number of valence electrons. For example, for sodium we said 1s2, 2s2, 2p6, then 3s1. Highest n in this case equal to 3. That one is going to give you the period of the element. Group, which is equal to valence electron, is going to be, you look to the highest n, we have only one orbital, and it's the s orbital. I have only one electron, that's one electron. Core electrons will be equal to those 2 plus 2 plus 6, 10 electrons. Okay. One example, one more. Let's go with silicon. 14. 1s2, 2s2, 2p6, 3s2, 3p2. Highest n equal to 3. So this element belongs to the third period. Group, which is equal to valence electrons. I have two orbitals that belong to n equal 3, s and p. Add the electrons. 2 plus 2, 4. This element, silicon, belongs to the group 4. Okay, the fourth group. How about core electrons? Core electrons, what we're left here, 10 electrons. If you want to write a short electron configuration for silicon, it will be neon, 3s2, 3p2. One thing that you need to keep it in your mind, that when we write electron configuration in a short version, we keep the valence electrons or orbitals that carrying valence electrons out. You do not include last layer inside, inside the the noble gas, or I mean do not add them to the noble gas. Okay, you need to keep them out, because that way I can simply look to them and say, hey, neon is belong to second period, n equal 2. So 2 versus 3, this one has higher n because it has higher n, so the n is going to be equal 3, the period is going to be 3. Now that I figured that I have two orbitals with n equal 3, I need to add the electrons. 2 plus 2, the group or valence electrons equal to 4. 2 plus 2. Lithium, we said 3, it will be 1s2, 2s1. Helium is 1s2. Okay. Short electron configuration of lithium, it will be helium 2s1. For lithium, you don't have any option, because this is the first noble gas. Okay. This is the first noble gas, so I can write, helium again. How about this? Neon. Neon is 1s2, 2s2, 2p6. Short electron configuration for neon, you go with the previous noble gas. Previous noble gas, or the noble gas before neon, it will be helium. and helium will take 2 electrons. So now you go with 2s2, 2p6. Highest n equal to 2. So the period belong, or this element belongs to 2, second period. How about the group or valence electrons? It will be 2 plus 6, 8. Core electrons, only one s with 2 electrons. So you will have 2 core electrons. So till now I was talking about element that belong to main element, or element that's bringing s or p as last orbitals. Okay, we can switch to d orbital or transition metals, but before we switch to that one, let's talk about adding or subtracting electron from main element, and then we switch to transition metal. Okay, what's the electron configuration when it comes adding or taking electron? I go with this one. Let's say we have nitrogen, 1s2, 2s2, 2p3. Last orbital is the p orbital. It has 3 electrons. It has 3 electrons. You want to add electron to it. So if you add 1 electron, it will be -1. In that case, it will be 1s2, 2s2, 2p, 3 plus 1, 4. So last orbital, go 1 in each. And now you don't have option. The fourth one, you have to pair it. You want to take electron, you take it from the highest orbital. Okay. You take the electron from the highest orbital. You go with 1s2, 2s2, 2p, 3 minus 1, it will be 2. So we have only 2 electrons this time. Okay. When it comes to main element that they have s or p as the last orbital, you add or subtract electron, you add or you take electron from same orbital, technically the last orbital, which is, in this case, is the p orbital. You add or you take electron from the last orbital. So we're dealing with the same orbital. Okay. Now I want to switch to transition metal, and when we are talking about transition metal, the last orbital is going to be a d orbital. Okay. So transition metals, last orbital, it will be a d orbital, and it will be n minus 1 d orbital. We go with iron, 26. You go with 1s2, 2s2, 2p6, 3s2, 4. No, yeah, 3s2, and then we go with 3p6, and after that one we go with 4s2. Now n minus 1 d, so it will be 4 minus 1 d. Total I have 26 electrons. I use 2, 4, here 10, 18, 20, so I'm left with 6 electrons, so the last orbital it will be 3d6. Argon is equal to 1s2, 2s2, 2p6, 3s2, 3p6. How can I write iron? How can I write iron? Or how can I write the electron configuration of iron in a short version? I'll look to the periodic table and I find the noble gas before iron. Noble gas before iron is argon, and this is the electron configuration for it. So for iron, you can go with argon, which is representing 18 electrons, and keep rest. So until 3ps, we're writing them as argon. Now we go with 4s2, 3d6. Remember, I told you when we write the electron configuration, we try to keep the orbitals that representing valence electrons or carrying the valence electrons out. Okay, and I kept 4s2 and 3d6 out, and those are orbitals that carrying valence electrons. Okay. When it comes to transition metal, if you want to find valence electrons, you go with S plus D. S plus D. Okay, S plus D, except when D is full. Okay. So for iron, we said argon, 4s2, 3d6. Highest N in this case is equal to 4. So iron belongs to the fourth period. Valence electrons, which is equal to group, it will be 2 for 4s plus electrons of D. D we have 6 electrons. So iron belongs to group 8 of the transition metal. How about core electrons? Core electrons equal to argon equal to 18 electrons. Okay. So when it comes to transition metal, you add electron of S to D, except when D is full. Okay. Zinc atomic number is 30. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d10. Highest N equal to the period equal to 4. So zinc belongs to the fourth period. Valence electrons equal to group. We were supposed to say S plus D. So we go with 2 plus 10. It will be 12. Is it wrong to say it? No, at all. It's completely correct. But some they said when D is full, ignore it. When D is full, ignore it. So, is it fine to say, because D is full, it has 10 electrons, I should not, consider it and say just 2 as a valence electron? That one also is correct. Okay. Which one is correct? Frankly, I saw both of them. If you look to your lab manual, in Let me check and see whether I have a lab manual here or not. Okay. Okay. I don't know whether you can see this one or not. For zinc, it says group 2, 2B. Why 2B? Because we are talking about transition metal. We want to say this is different than this group. So it says 2B, and here is 2. They did not consider the 10. But also, we say 12. 12 for zinc. So we can have 2B or 12. You can add 2 plus 10, make it 12. Or you can ignore the D because D is full and say just 2. Which one is correct? Both of them. Both of them are correct. And again, it depends like who's grading. I'll say when it comes to me, I will accept both of them. But be careful when it comes to online system. Online system might, by chance, might that, you know, like say, okay, because D orbital is full, so the group is going to be equal to. Be careful about that one. But you can use, you know, any of them when it comes to a hard copy. How about core electrons? It will be equal to 18. 18 core electrons. Okay. 18 core electrons. If we go with 12, it will be 18. Otherwise, if you go with, you know, 2 as a group, the group or valence electrons, that means you're ignoring the D. If you're ignoring D, then you will have 28 valence electrons. Now I want to add or take electron from transition metal. And let's say we have nickel, 28 electrons. And the electron configuration, it will be argon, 4s, 2, 3d, 8. I want to take electron from argon. Let's say take just 1 electron, plus 1. You take the electron from the highest N. Okay, you take the electron from the highest N. Be careful, please. Highest N. Highest N is equal to 4. So you will take the orbital from 4s, not the 3d. Not the 3d, because this one, it has N equal 3. So for nickel plus 1, it will be argon. And we take the electron from the highest orbital, which is S. Highest N, I should say. Highest N. It will be 2 minus 1. 1. And the 3d, we will have 8 electron in it. So nickel plus 1, it will be argon. 4s, 1, 3d, 8. How about nickel plus 2? It will be argon. 4s, 2 minus 2, it will be 0. So this orbital, it will be gone. We'll have 3d. So it will be argon. And then 3d8. You take the electron from the highest N. And in this case, is the S orbital. What if you want to give electron to nickel? You have argon. 4s is full, already has 2 electrons. 3d, it has only 8 electrons. So we have two orbitals and they are not full. We can give them, two electrons. This one, it says +1, so I can add one electron to D, and one electron I will put it there. Pair this orbital, so it will be argon 4s2 3d9. So as you see, adding or taking electrons are not happening from same place. When we take electron, we take it from the highest n. When we add electron, we add it to the first available orbital. First available orbital is the D orbital because it is not completely full. Okay, so now that I know how to add or subtract electron from transition metal, I want to talk about two facts: paramagnetic versus diamagnetic. Electron configuration of iron, we said argon 4s2 and 3d6. Sorry, yeah. There's one electron there. 6 electrons we have. If you have one orbital that is singly occupied, just one orbital, okay. If you have more than one, then that's perfect. But if you have just one or more, singly occupied orbital, we say that element is paramagnetic. When you put it close to a magnet, it will interact with external field of the magnet. Because I have 4 unpaired electrons, this element, it will be paramagnetic. Paramagnetic because I have unpaired electrons. I have 4 unpaired electrons. 4 unpaired electrons. But if you draw or write the electron configuration for zinc, it will be argon 4s2 3d10. Last orbital, which is the d orbital, is completely full. We don't have unpaired electron. So this one, it will be diamagnetic. Okay. How many electrons do I need to have the element paramagnetic? One or more, enough to make the element paramagnetic. And diamagnetic, you do not have any unpaired electron. Okay, we do not have any unpaired electron. Last thing about the electron configuration is going to be the exceptions that sometimes we are dealing with them. And you will see those for chromium or copper groups. Group 6 of transition metal, and also group 11 or 1. For chromium, that has 24 electrons, expected is argon 4s2 3d4. But in reality, we have this. We have 4s 1, 3d, 5. For copper, expected is a 4s2, argon 4s2, 3d, 9, but we see argon 4s1, 3d, 10. Anything under copper or chromium will have same electron configuration, like either copper or chromium. Let's talk about this too, why we see such exception. What's happened here? Why one electron moving from s to d orbital? In quantum mechanics, if you have one orbital that is full, or let's say here p orbital, we say this orbital is stable. Why? Because it's completely full. Or if you have a p orbital that it has only 3 electrons, not 2, not 4, only 3 electrons. Again, this orbital is a stable orbital. We say there is a symmetry. Okay, there is a symmetry. All orbitals are at least half occupied. So there is a symmetry, and because there is a symmetry, that orbital, it will be stable. It will make the system more stable. And when it comes to chromium, with 24 electrons, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We're supposed to have 4s2 and 3d4. That's expected. That's expected. This is not correct. Okay. So last orbital is here. Before the last one, we have 4s with 2 electrons. Then we have the d orbital that it has 4 electrons in it. We say, if you rearrange this one and write it like this, take 1 electron from the s, send it to higher orbital, and then flip the electron. Flip the electron. That one, it will give you 2 orbitals, s and d orbital, that they are singly occupied, and all will be stable. Okay, because there will be symmetry in both s and p, or the d orbital. So bottom line of this, quantum, if you have a full orbital or singly occupied orbital, that orbital, it will be stable orbital. When it comes to chromium, I need 1 electron, just 1 electron, to make the d orbital half occupied. And because it's half occupied, it will be stable, and it will release some energy, and that energy, it will pay off whatever we spend to move the electron to a higher level. Okay, so the stabilization that we get through symmetry is higher than this energy, and that's the reason chromium preferred to be 4s1, 3d5. Okay, because symmetry is making it more stable. When it comes to copper, with 29 electrons, supposed to be argon 4s2, 3d9. So the last orbital, is a d orbital with 9 electrons. And here also we have the 4s orbital with 2 electrons. 4s orbital is fully occupied. So there is symmetry for it, but the d orbital is not. If you give it 1 electron, you will have 5 orbitals that they are full. So you will get good stabilization by making the d orbital full. And I'm going to give 1 electron to d, then the 4s, it will have only 1 electron, and d orbital you will have 10 in it. So now d orbital, which is made of 5 boxes or 5 orbitals, is completely full. You will get good stabilization when it comes to d orbital. How about the s orbital? Is half occupied. Also, we get some stabilization here. Okay. So this system now, it will be stable. Remember, we had to spend this energy, but we get some energy here by making the d orbital fully occupied. And this energy, if we call it E2, E2 is higher than E1. So that's the reason the copper preferred to be argon, 4s, 1, 3d, 10. So for copper, for chromium and copper, we will see that exceptions. If you can give 1 electron to d orbital to make it either half occupied or fully occupied, then do it just by 1 electron, just 1 electron. You cannot do it with 2 or more, because then the energy that you are spending to move the electrons will be so much that you will not get it back by stabilization or forming symmetrical orbitals. You will not get it. So only for 1 electron. You are allowed to transfer only 1 electron. Do we have such a thing when it comes to f orbital? Yes. For f orbital, if you give f orbital 1 electron and you make it half occupied, or make it full occupied, then do it. Okay. So for f orbital also is possible. That means when it comes to something like, say, 6s2, then we should have 4f. This one will be, let's say, 6. This is the expected. And here can have, I believe it's xenon. Let me check the periodic table. And yes, xenon. Okay. Xenon 6s2 4f6. This is expected electron configuration, but the real one, it will be xenon 6s1 4f7, because this one, it has only 1 electron, and now the f orbital is made of 7 boxes. It will have 7 electrons. So now this f orbital, it has symmetry, and because it has symmetry, it will make the system stable. So you can get this electron, this type of electron configuration when it comes to f orbital. You can transfer 1 electron and make the system stable. Again, those exceptions are possible for at least n equal 4. N equal 4 or higher, you can have such exceptions. You cannot see it for n1 to n3. Don't do it for, like s and p orbital. That's not going to happen. The gap between orbitals so big that you will not get it back by stabilizing the orbitals. From n equal 4 or higher, we can have electron transfer between s and d or s and f orbital. And I'm gonna stop here, and next time I will go through a trend inside periodic table, and I will show you what's the trend when it comes to size, ionization energy, and electron affinity, and also metallic character. Have a good time, guys.